In this lecture, we're going to start talking about the magnetic field. So, a magnetic field exerts a force on a moving charge. So in order for a magnetic field to basically work, you have to have a charge, and it has to be in motion as well. And the direction of force is determined by right-hand rule. I'll get back to that in just a second first, right? So in order to understand how this works, right, let's just start writing down what the force is. So the force is equal to Q V cross B, okay? So let's basically put down everything. This is the force here. This is the charge. This is the velocity. And this is the magnetic field. And this funny thing here is the cross product. All right. Okay, so I'm going to get into describing what this right-hand rule is in just a second. All right. What you'll notice is that both the velocity and the magnetic field is a vector product. So we should make a note that the magnetic field is in fact a vector product, a vector, right? Which means that has both basically a scalar part, a magnitude, and a direction as well. All right, so let's get the units of this thing. So units are basically, let's just write this thing down. This equation is basically force is equal to charge times velocity. Charge, velocity times basically magnetic field. So basically the units is units of force is equal to units of charge, units of velocity, units of magnetic field. All right, this is what I want to find. So forces in newtons. This is equal to basically charges in coulombs. This is in meters per second, and so this units of B is basically means that B is equal to newtons over coulombs, meters per second, right? And so we give this a special name. This is called a Tesla, Tesla, or T for short, right? Now, part of the issue is that T is a large unit, right? For most of the things that we try to do basically on Earth, right? So for instance, the Earth's field that's about 10 to the minus 4 Tesla. A strong magnet that's about 0.1 Tesla. And the strongest magnet, this is magnets that can be produced on Earth. These are like maybe a magnet that is an MRI machine, for instance. That's about 10 Tesla or so, right? Okay. So a lot of times we also use unit. Gauss, which is G, that's about 10 to the minus 4 Tesla. Right? In case of any one of you ever have your own electric car company, maybe you should call the next one a Gauss or something like that. All right. Okay, so let's talk about direction, right? And in order to do that, we're going to have to construct a picture of this, okay? So suppose you have a charge Q with mass M, right? Moving through a B field, right? The B field is the magnetic field, right? So I'll draw a picture here. So draw basically, this is my velocity, my charge Q, M, it moves in the velocity V. I'm going to draw the B field as basically coming out of the page. That's my B field, right? And now I want to figure out what the force is, right? So the force, or at least figure out the direction of the force, is QV cross B, right? So what is direction of F? Okay, so for this, you can use the right-hand rule. Okay, so we use right-hand rule. Okay, and so the way you construct this is that basically, let's look at how the equation is written. All right, so V cross B. All right, and so you imagine right hand. Okay, thumb points in the direction of the first thing. Thumb in this direction. Okay. Fingers point this along the second thing. And then this is the arrow sticking out of your hand. Out of palm. Okay? So if I were to draw this right hand rule, okay, I can imagine that my my thumb points in the direction of basically the velocity, right? So that's my thumb. My fingers, right, point basically in the direction of the B field. The B field is coming out of the page. My fingers point this way, and my palm, the force is going to become an arrow that comes straight out of my palm, right? So if I take my hand here, this is my thumb is pointing in this direction. My fingers are coming out of the page, and there's an arrow sticking out of my palm like this, and that's the direction. So in fact, the force is down. Right? So this is the way you can do it for basically determining the direction of the force. Okay. Now, what's interesting about this right, is that the force is perpendicular to both the velocity, the B field, and V, right? Velocity as well, right? So basically it's perpendicular to the motion. This will become important in a little bit, right? Okay, so now the magnitude is, so V cross B, that is going to be V times B sine of theta, where theta is angle between V and B, right? So in this previous example here, if you were to look at from the top, so let's draw the line like that. right? Then this is angle here is the angle between the velocity vector, which is pointing this way, and the B field. This is angle theta here. And in this case, this is equal to 90 degrees, right? Because they're at right angles with respect to each other. Okay? Right? This will also be important later, right? So for the previous example, theta equals 90. So that means sine theta equals, 1. Okay? Now you're going to get something very interesting, right? If V and B are in the same direction, then the angle theta is 0. Sine of 0 is actually 0 in that case, right? So you actually don't have any magnetic forces if the B field direction is the same direction as the direction of motion. Okay, so we wrote that the force is going to be equal to QV cross B, all right? We also know that basically it's because it's 90 degrees, the magnitude F is equal to QVB sine theta, which we just derived because it's 90 degrees, is just QVB, okay? Theta equals 90 in this case. All right. Now, if this is the only force, this is also equal to F net, the net force, and that's equal to mass times acceleration, right? So, if we draw what this thing looks like, this is velocity, right? This is the mass of that particle. There's my force here, right? The force is at 90 degrees. It will cause this thing to basically fly around in a circle, okay? Because the force is perpendicular to the direction of motion, right? So, this means that ma is equal to m times ac. So centripetal acceleration. Right? Which is mv over r, whatever r is the rate of circulating and flying. And so it's equal to now, because it's equal to F net, is equal to QVB, right? And so basically what this implies, you solve for R, gives you mv divided by qb, right? And so this is the radius of that circle that it moves in. And this has a special name associated. It's called the Larmor radius. The Larmor radius. All right. The period of the orbit, the time it takes for it to complete one circle, that's t. Well, that's just basically the total distance, L over V. And what's the total distance? Well, it's the total distance of a circle, that's 2 pi times r divided by V. And you basically work this out. It's basically 2 pi m over qb, all right? We'll notice now that this is independent of v, right? So the Larmor period here does not depend on the velocity, right? Okay. So let's give a little example of this. Okay. So suppose you have a period of electron around strong magnet. So in that case, B is approximately 0.1 Tesla or so, right? Q is equal to basically 1.6 times 10 to the minus 19 coulombs. And the mass of the electron is 1.6 times 10, hold on, sorry, pair of a proton. Sorry, 1.6 times 10 to the minus 27 kilograms. Okay, so now this is the period is equal to, let's work this out, 2 pi m over qb. Let's just plug everything in. That's basically 2 pi 1.6 times 10 to the minus 19 divided by 1.6 times 10 to the minus, this is the mass is 27 up here, and that the charge is minus 19 down here, 0.1, okay? So this is basically 2 pi times, that's why I chose this number, it's 1.6 on for both the constants cancel each other out, times 10 to the minus 7, right? Which is 6.282 times 10 to the minus 7. And so that works out to be roughly about 0.63 microseconds, right? Okay, so that's interesting, all right? Now, here's another thing which you can go ahead and compute now, all right? Okay, now suppose you have a bunch of charges moving at 1,000 kilometers a second, all right, which translates to be 10 to the 6 meters per second, right, into a 0.01 Tesla field. Okay. Okay, so let's draw a picture of what this looks like. So first thing we'll start out with is that we have a bunch of particles. Now they're going to hit this field, and I'm going to point this field upward already. This is my B field. And these particles are going to basically be curving downward as we go down at this thing, all right? Okay? And when they hit this B field, they're going to basically move its direction along the X direction here, say. Let me just see what I'm trying to do here. Right, I see what I'm trying to do. Okay, so that if this moves, penetrates 0. What did I write here? I want to write 0.5 meters in the X direction. How much does it drop? Okay, so you can imagine basically how to do this problem here. So you can imagine that I come in, all right, this thing starts to bend. This will have some radius of curvature here given by the Larmor radius, right? And after it moves a certain distance, basically let's say this distance is about 0.5 meters, right? This will drop down in the y direction by some amount, delta y. I want to basically compute how much it drops down in the y direction, how much it drops delta y. Okay, let's go ahead and do that. All right. So first, let's compute the alarm radius. RL is equal to mv over qb. This is from the previous page. Okay, and I'm going to basically keep everything else as well, right? Charges, let's say protons. Okay, so in that case, the mass is 1.6 times 10 to the minus 27. The velocity was 10 to 6 divided by Q is 1.6 times 10 to the minus 19, and then the B field is 0.1 Tesla, so 10 to the minus 2 Tesla or so. Okay. And now the reason why I picked these numbers is because if you actually work this out, this is exactly 1. That's 1 meter. Okay. Now, as the thing moves along the x direction, I can imagine that this thing moves at about half this distance, 0.5 meters or so. So this is an angle associated with that. Okay. So basically, x, which is equal to 0.5, is equal to RL sine theta. Okay. RL is 1 meter, so 0.5 equals sine theta. That means the angle it sweeps out is basically theta is equal to 30 degrees. Right? If you basically just apply the inverse sine to 0.5, that's 30 degrees or so. Right? And so basically this distance delta L that it drops, delta y is equal to, well, it starts out at y0, okay, right, minus y at 30 degrees, okay, and y0 is basically y at 0, okay, at theta equals 0. Okay, that's at that point, minus y at theta equals 30 degrees. Let's work that out. That's going to be RL cosine theta, right? Evaluate theta equals 0 minus RL cosine theta again. Evaluate theta equals 30, right? So this is just going to be 1 RL minus RL cosine of theta of 30 is 0.866, right? So you can work it out. This turns out roughly to be, and RL is 1, 0.134 meters is delta y. That's the drop, right? Now, what's interesting about this is this process can be used to separate out different materials from each other. And not just different material, I'll say different elements. Or actually the right word is actually isotopes. Okay? So suppose you have two different isotopes, right? I'm going to basically call this nickel 56 and the other one and nickel 60, all right? So these are nickel, so that means they have 28 protons. But the difference is this has, let me say, this 28 neutrons. And this one has, let me if I do it right, 4 more, 32 neutrons, right? Chemically, these things are identical because chemistry is determined by the number of electrons you have, and the number of electrons you have is determined by the number of protons you have. So chemically, you can never separate these two things out, right? So basically, there are several ways of separating this stuff out. One way is to basically use something called electromagnetic separation, what this thing is using. The other way is basically you could take advantage of the fact that these two weigh slightly different amount, and you can put them in a gas centrifuge to do it. So this sort of separation was actually very important back in World War II when the Americans were starting to build the first atomic bombs. This was a way of separating out basically uranium-238 from uranium-235. Uranium-235 can be used to make nuclear weapons. Uranium-238 cannot be, right? Okay, so let's see how this works, basically. Right. So that means there are 60 protons plus neutrons, and neutrons roughly weigh the same as protons. Very tiny difference. And this is 56 protons and neutrons. All right. So the mass of this particle, well, that's just basically 56 times the mass of proton, 1.6 times 10 to the minus 27. Okay, did I write down what the number is? No, but I'll just keep in mind what it is in a second. And this mass is going to be 60 times 1.6 times 10 to the minus 27. Okay. All right. Okay. So what we're going to do is we're going to accelerate this stuff, right? And then basically put it through a magnetic field, right? So let's accelerate. So basically you accelerate them, you put them through a potential drop here. This is basically delta V or V. And I'm going to just choose 10,000 volts, right? So 10 to the 4 volts or so, okay? All right? And now I'll apply the same B field, or actually a different B field. All right, put it in the B field now. The B field will be 0.1 Tesla. So these particles will accelerate here to come with some final velocity, which I don't know what it is necessarily. And then it's going to basically be bent, all right? And by the time it gets bent, I'm going to ask the question basically, what's the difference between two? So we're going to get basically two particles. We're going to be very similar, but there's going to be a difference between these two. This is delta X, all right, between 56 nickel and 60 nickel, right? I'm going to go ahead and compute what that is, all right? Okay, so first thing, let's get the velocity for each one. So velocity, right? Well, how do we get that? So I'm going to basically set 1/2 mv squared, that's kinetic energy, that's equal to gain potential energy, Q delta V, all right? So that means it's basically the velocity is equal to the square root of 2 over m q times delta v. Okay, so first thing you will notice, right, is that basically the velocity depends on what the charge is, but also depends on the masses. So nickel 56 and nickel 60 will have slightly different velocities with respect to each other. Okay. Now, next thing, let's get the Larmor radius, RL. So you can imagine this separation here is the difference in the two Larmor radius of the two. This is equal to mv over qb, right? And I know what v was, so we just plug that in. So let's write this thing. This is m over qb. Q for both of the same, it's just basically 28 times 1.6 times 10 to the minus 19. Times the velocity here, this is the square root of 2 over m q delta v. Delta v is basically 10,000, which is what we just said earlier. All right. Okay. So let's simplify this a little bit. This kills off that, because that's square root. This makes this a square root. So let's basically write this thing down very simply. This is 1 over b square root of 2m over q delta v, right? Okay, now I'm going to write basically q is equal to 28 times 1.6 times 10 to the minus 27. I'm going to denote this by z, okay? Z is going to be equal to 28. So another way of writing it is basically q is equal to z times 1.6 times 10 to the minus, oops, sorry, it should be 19, minus 19 coulombs, that is, right? And similarly for the mass, this should be basically either like 56 or 60 times 1.6 times 10 to the minus 27. I'm going to basically call this A is equal to 56 or 60, which gives me M is equal to A times 1.6 times 10 to the minus 27 again. All right. Okay, let's plug everything in now. So RL is equal to 1 over B square root 2A in the M part, the Z on this part now, 1.6 times 10 to the minus 27, 1.6 times 10 to the minus 19, okay, and then delta V is 10 to the 4th, and I'll just write this one down to 0.1, all right, so now we're done. If I go through all of it, this is roughly 0.1 times the square root of 2A over Z. Okay, so that's why I wrote it this way, because now I can just plug in these values here at the very end and get the answer here, right? So let's write this thing down then, okay? So this turns out right. This turns out that this is roughly, right, 0.2 meters for 56 nickel, and for nickel 60 is 0.207. Write that more neatly there. 0.207 meters for 60 nickel, right? So that means that, sorry, it's actually the 007, sorry. Okay, so the difference, delta RL, is 0.007 meters, which is 0.7 millimeters, right? Difference. And 0.7 millimeters is not something you can't measure, right? Like you take a ruler, precise enough ruler, you could get that distance basically. And so this is something that you can actually do to sort of separate stuff out. Okay. Now, we've been thus far dealing with basically individual charges, right, and the forces on them. So now let's basically look at basically a torque on currents, right? And let me just see. I should write. Yep. Okay. Right. Okay. Right. Torque slash forces on currents, right? So rather than having just one charge moving, I want to have a bunch of charges moving. Okay. All right. Now suppose you have a current in a wire. Okay. So what does these currents do? You have some length here, L, a bunch of charges Q in there, and these charges basically steadily moving in this direction at some mean velocity. Okay. Right. So the force on each charge Q is going to be basically Q V cross B. Okay. And the total force, right? If this thing was contained in a wire, say, right? That's the sum over all the forces on all the charges. That's going to be basically the sum of Q V cross B. Right? Now, okay. Now let's keep it simple. Okay. Suppose they're all moving at the same speed. Okay. Suppose Q and V are all the same. Okay. So if they're all the same, all right, I could write this as just basically, these are just constants, right? So it's basically the sum over the total number of charges. So N total QV cross B, right? Okay. So now, what is N total? N total is the total number of charges. Total number of charges. Okay? What is a way we could write the total number of charges? Right? Well, let's redraw that wire again. There's a certain distance, L here. There's a certain area, A, on the cross-section of the wire, right? And there's a certain density of charges, basically. So there's a N is the number density of charges. So the total number of charges, well, that's just basically the number density of charges times the volume, which is the number density of charges times the cross-sectional area times the length. All right? So that means the force, which we just wrote as N total, QV cross B, that's just going to be equal to N AL Q V cross B. All right? Now, what we notice here is that V times this, times this, times this, that's just the current, all right? So I, the current, that's equal to N times the cross-sectional area times the charge times the velocity, right? You can think of it that way, all right? I'll write without that velocity there, okay? And if V is moving along the wire, right, I can rewrite this as the force is equal to I L cross B, where this is the direction along the wire. All right. Okay. So that's brilliant. So this is basically the force for a wire. Force on a wire. Okay. So the next thing is now let's consider loop. Okay. A loop's not all that different. I'm going to draw it like this. Draw a nice square loop, all right? Okay. All right angles is supposed to, rectangular, or all right angles is supposed to each other. This thing has a normal vector sticking out of it. That's n hat. All right. And I'm going to put a B field. But I'm going to put the B field in a funny way. I'm going to put a line along the XY, along the XZ plane. Right? That's my B field right there. Okay? Right? Is in XZ plane. Okay, let's call this one X. Call that one Y. I'm not even sure this is correct. It's actually fine. And this is N hats along the Z hat direction, right? So this thing's not sticking along the side here, it's just sticking. And there's going to be an angle between these two of theta, right? Okay. And what I want to do is I want to consider what are the forces doing on this particular loop here, right? So I'm going to consider this one has a certain length here in this direction, L, and a certain width in this direction along Y of W, all right? Okay, so now I'm going to basically just consider all these different things, all right? So there's a force for the first wire, a force for this wire, a force for the third wire, and a force for the fourth wire. Okay? All right. So let's draw out the directions for each one of these things here. Okay. The force for the first wire, force for the second wire, force for the third wire, and force for the fourth wire. Okay? I'll come back to this thing in just a second. We'll just compute each one in turn. All right, so let me see. What's the easiest way of doing this? Yeah, let's do it this way. Okay. We'll do F1 first, all right? Okay, so let's write down the force equation. F is equal to I L cross B. Okay, so first thing, what's the angle between this length? Oh, I got to pick a direction which the current flows. So current is flowing this direction like that in a counterclockwise direction. All right, so let's basically first figure out which direction this thing goes in first, right? So the first thing we will notice is that we use the right-hand rule, right? The angle between basically this thing here, which is along y, and B, which is the XZ plane, is 90 degrees. So in this case, the theta between these two is 90 degrees, all right? So first of all, this is just going to be I times L, or times, not L now, in this case, is going to be W. I times W times B, all right? Now let's get the direction of this thing, all right? The direction, we use the right-hand rule, okay? So let's see. So I need to point my thumb along the current wire, good. My fingers are going to be pointing basically along the B field, which means that the force is going to be in this direction, like that, okay? So, let me just see how I'll do this. You know something, I'm not gonna, I'm actually gonna go back to this in a second, all right? I wanted to make one point first, right? And that's the following, okay? So, all right, so I'll come back to this just a second. Now the torque, okay, tau is equal to R cross F, right? And this is just going to be, for the wires, R cross I L cross B, right? Okay. And so this is equal to R cross L times I cross B. Okay. Now look at this thing very carefully, right? What's R cross L for each one of these things here? Right. So if R is something we pick from the center to each one of these four wires here, all right, okay, then let's see, so let's just do this as R cross L, all right? So R is going to be pointing along for wire 1, it's going to be pointing outward. L is pointing basically along the direction of current, so that points outward, so it's basically in the anti direction. Similarly, along here, basically, right, R is pointing upward here, the current is flowing this way, again, it's pointing up again. In this direction, it's flowing downward, it also points along n hat as well, and so is true for this one, right? And so, what this gives me is that this is actually equal to R R times, let's see, so the length of this one is going to be W, all right? So in fact, it actually should be, right, it should be L over 2, right, that's the distance from the center, right, times W, okay, for wire 1, okay, and then plus the second term is going to be W over 2 times L, as for, this is for the third term, that is, plus now, this next term is going to be L over 2 times W, that's for the second wire, plus W over 2 times L for the fourth wire. They all point along the normal vector I cross B. There's no dot there, right? And so this thing here, right, if you do it correctly, right, there's one more factor here which is missed, but this should be equal to the area, right? So this could basically be I times A n hat cross B, right? And so this gets a special name, right? This is called the magnetic moment, right? Which I'm going to define as mu, which is equal to I A n hat, right? And so what's nice about this is that this is going to be equal to the torque here, right? And for n turns of a loop, tau is equal to sum of each, n turns of a loop, mu, which is the vector here, is equal to the sum of each mu for each loop, which in most cases is going to be basically n times I A n hat, right, for n turns. Okay. Right. Now, I wanted to make one point about this thing, all right? And that is basically we're going to look at all the directions. It won't actually solve it directly yet. We'll just look at the directions of this. So this points downward, okay? Again, I could put the same thing here, right? So I could basically do on this one, on wire 2 here. And in that case, it points downward, and my B field is pointing up in this direction, slanted up. And so this force will feel force in that way. Along here, if I compute that correctly, right, this is going to be perpendicular to the flow. This, I believe, points outward like this. This points outward like this. So you see what happens is that the force causes the entire wire, the entire loop, to rotate in this direction, right? So that's essentially what happens with the torque of this object, all right? Okay, so what we're going to do is going to redraw this one and actually compute this thing in a way that actually makes a lot more sense, all right? Okay, so let's first redraw this thing again. Okay, again, a torque on a current loop. Okay, and we're going to make contact with basically what we just derived earlier for the torque here. So that's just basically equivalent to mu cross B, right? We're going to basically make contact with that in just a second. All right, so for the torque that we discussed, basically, there's only two pieces that connect to the torque. That's this is based on F1 and F2, right? And if you compute this correctly, this is they both are equal they're equal in magnitude, but just opposite direction, right? So they'll torque it in both sides, they'll add the torque correctly, right? Okay, so what I'm going to do, I'm going to basically redraw everything, right? And we're not going to consider the ones on the side, right? Because just to make our lives a little simpler. All right, so let's see. So there's my normal vector here. There's my angle of the B field. Theta again. All right, and so the force is equal to IL cross B, and the torque, tau, is going to be equal to, I'm just figure out it on just one of them, tau of wire 1, and then it's going to be the same for wire 2, right? Okay, so that's just going to be, let's see, this is L, this is W here. This tau here is going to be equal to R cross F1. Okay. All right. So let's get the B field, right? So I said the B field earlier was in the XZ plane. So this is X, that's Y, that's Z pointing upward. Okay. So the B field, right, is going to be written as B sine theta in the X hat direction, right, plus B cosine theta in the Z hat direction, right? So that's basically B. All right. L for 1, well, that's going to be pointing in this direction. That's going to be W times Y hat. Good. I is going to be whatever I is going to be. And then R1, let's say R1, that points from here to there. Okay. That's just going to be equal to, that points along the X hat direction, and the distance is essentially L over 2, right? Maybe I'll convert this to a little L just to make sure we don't get confused between the different L's and stuff. All right. Okay. So let's go ahead and compute this thing. Tau is equal to R1 cross F1, right? That's going to be equal to, so let's do each one at a time. This is L over 2 X hat cross I. Let's see, L1 is W Y hat cross now the B field. That's just some B here. Sine theta X hat plus cosine theta Z hat. Okay? Right. So let's multiply this thing out. That's going to be bring out all the numbers out. So that's going to be I here. There's a W here. There's an L here. There's a 2 there. There's a B there, right? And now, let's see. This is X hat cross Y hat cross X hat sine theta. That's this first term, plus X hat cross Y hat cross Z hat cosine theta. That's the second term. All right. Okay. All right. So we have to know what these things look like. So basically, the way we compute this is that we just start out with X hat cross Y hat equals. So let's see if it's X direction, Y direction. Oh, Z direction is correct. So that's basically Z hat. Okay. This is universally true. If you have a correctly oriented coordinate system, this must always be true, right? And then what's interesting about this is that if you reverse these two, Y hat cross X hat, so basically you point Y hat along here, X hat across there, you point downward now, okay? This is minus Z hat. So basically when you flip them, you basically get a minus sign there, right? And then what's also interesting about this is that as you basically move the entire thing over, so Z goes there, Y goes there, X goes back to the bottom, you basically get the right answer again. So the Y hat cross Z hat equals X hat, and then move one more time. Z hat cross X hat equals Y hat. All right? Okay, and then we flip them again. Z hat cross Y hat equals minus X hat, and x hat cross z hat equals minus y hat, right? Just a few things that you need to know, right? Okay, so we got to do these first, right? So this thing is y hat cross z hat, that's minus z hat. X hat cross minus z hat, that's going to be minus y hat, but minus sign is y hat. So this is basically y hat, is the right thing here. And this one is going to be y hat cross z hat. Y hat cross z hat is x hat. And x hat cross x hat is 0 actually. So x hat cross x hat equals 0. The same is true. Y hat cross y hat equals 0. Z hat cross z hat equals 0. Any vector across itself is always 0. Okay? Okay, so this entire thing is 0. Right? So basically left, just tau 1 is equal to IWL over 2B y hat sine theta. Okay? Okay, so that's the torque. And then basically same for tau 2. Okay? This is also the same, IWL over 2B y hat sine theta. And so that implies tau is equal to tau 1 plus tau 2, right? That's IWL y hat sine theta, okay? Now, what is, I should write this a little more cleanly. IWL y hat sine theta, right? Now, you might ask, basically, what happens to these wires here? These wires here basically will cancel each other out. And actually, they essentially have no, well, that cancels each other out. But they'll cancel in force, but then the torque will turn out that their force and their radius in the same are in fact the same direction. And so when you do the cross product, there's no torque that comes from these two wires here. Okay. What's interesting about that? If we look at what we had just computed, I said the torque was mu cross B, right? So the torque was mu cross B is tau. Well, what's mu? And mu is equal to A n hat, IA n hat, right? And so, if we look at this thing, this is tau is equal to I times A n hat cross B, okay? That is I, A. Now, n hat is in the z hat direction, cross with B up here, which is B sine theta x hat plus B cosine theta z hat, okay? Z hat cross z hat, that's 0. So, and z hat cross x hat, z hat cross x hat, z hat cross x hat is y hat. I, A, y hat, B sine theta, okay? And what's A? A is just W times L. So this is equal to I, W, L, y hat, B sine theta. Look at this term here, and look at this term here. Whoops, sorry, not this term. This term here, okay? They're exactly the same. Right? Okay? So that's why this nomenclature is extremely powerful for current loops, right? Because you can compute these things very, very easily. All right. So, okay. Okay. Okay, so once you have it for one current loop, okay, so for n current loops. Well, that's just basically tau is equal to NIA n hat cross B. All right, okay. So this extends very easily, all right? And then, of course, basically, if you want to get the magnitude, n hat cross B, that's just B sine theta, okay? Where this angle theta, this angle theta is the angle between basically the n hat vector, the normal vector, and the B field, all right? Okay. All right. So let's use this technology. Let's compute calculate the magnetic moment of a circular loop now. All right, so we basically did the rectangular loop. Let's do the circular loop. All right, so you can imagine that I have some circle here, has some radius r, has some current flowing around it like this, I. This current basically has this loop has a, let's say normal vector pointing in this direction, say, okay? And let's say some B fields pointing this direction, pointing up, straight up, okay? All right, so let's go ahead and compute that thing first. All right, so mu is equal to, well, it's I times area times the normal vector. What's area? Well, that's a circular loop, so it's I pi r squared times n hat, okay? That's the first thing. Now, let's now suppose we have this B field and it makes an angle theta with respect to it. So now, suppose we have a B field at an angle theta with respect to n hat, right? Let's compute tau. Tau is going to be equal to mu cross B, right? Which is just going to be, let's get the magnitude, tau vector is going to be equal to mu, right? Let's see, so that's essentially going to be I pi r squared, okay? N hat cross B, let's take the magnitude of this thing. That's just going to be basically I pi r squared B sine theta. Okay? Pretty simple. Okay? And so for small theta much less than 1, sine theta happens to be roughly about equal to theta. Okay? You get that from Taylor expansion. Or you just basically know that this is true. Right? Tau is roughly equal to I pi r squared B times theta. Right? This little result right here for this case will be important in the homework. All right. Now, once you have it for a circular loop, you could do it for all kinds of things, right? So for instance, let's get the magnetic moment. So we can extend this to all kinds of round things, to a disk and a sphere, right? So let's get basically, let's see how that works, right? So for disk, okay, we'll just compute the magnetic moment here. Right. Let me imagine I have a disk with charge Q on it, and no, actually a better. I'll imagine a surface charge density sigma. Okay, this is a surface charge density. Okay, so typically this is something like Q over the area of this thing, but we're not going to worry about that right now, right? And I'm going to basically set this upon rotation, so this entire thing's going to rotate with some angle frequency omega now, right? And what I want to do is I want to compute what the magnetic moment of this rotating charge object is. Okay, so what is the magnetic moment? Right? Things don't have to be wires. They could just be like things that are just spinning around, right? So to do that, the magnetic moment d mu, well, that's going to be equal to basically the area times the differential current. So imagine you break them into tiny rings here, and each ring carries a current di in it, right? And this has some area associated with it inside of it. Okay. So the differential magnetic moment is this. So the magnetic moment mu is going to be integral of A di. All right. Okay. Well, what is di now? Di. Well, that's just basically the amount of charge in here, which is dq, divided time it takes basically for me to spin around, which is t, which is some period. And t is equal to 2 pi over omega. I'm spinning at this particular frequency here now. All right. So that's just going to be equal to dq over t, which is dq over 2 pi times omega, right? So divide this thing out, the omega pops on the top. All right, so now I got to figure out what dq is going to be. So imagine I have a tiny thickness to this ring, dr. So dq is going to be equal to the surface charge density times the differential area, which is surface charge density times the circumference of this ring, call this r here, dr. Okay, so let's plug this thing in now. Okay, so this is equal to integral of the area, okay, times di, which is dq over 2 pi, so it's omega over 2 pi there. Now dq is basically sigma 2 pi r dr. Okay, and I'll integrate this from 0 to, let's say the radius of this thing is capital R. Okay. Now, the one thing I forgot to mention is what's A. A is the area inside each loop. So this A here is just pi r squared, little r squared now. All right. Okay. So let's go ahead and do this now. This is going to be equal to omega over 2 pi. Okay. 2 pi here again. There's a sigma integral of pi r squared, r here again, dr. All right, lo and behold, 2 pi's cancel each other. This is r cubed, so omega sigma pi integral of r cubed dr, 0 to r. You can do this thing pretty easily. This is essentially going to be pi over 4 omega sigma r to the fourth. Okay. All right. Now let's do one more example of this. Okay. Let's do a charged rotating sphere. And so this is just going to be mu vector. And then it's just basically the whatever n hat's going to be, right? Charge rotating, sphere. Okay. So I'm going to basically take my sphere now. Let me think, what's the easiest way of doing this? Right. There's my sphere. I'm going to spin it along its axis with some angle of frequency omega here. Okay. And now, what is the way that I end up doing this thing? This is slightly tricky. Okay, I did a bunch of rings. All right, I wonder if disc is easier. This might be easier, but the problem is putting it all together. So I think I did a bunch of rings. Okay, so I'm gonna do it again. There's a bunch of rings here. Okay, so I want to find mu here for this particular object here. Okay, so how do I want to do this? So let me imagine that I'm going to break this up into a bunch of rings. Okay, they're more like ringish shells, basically. Right? Okay, and so let's see how I want to do this. This is going to be again d mu is going to be equal to a di times, let's say this is z hat direction. Let's see, z hat direction. Right, everything's always pointing in the right direction, so you can just sum them up correctly, right? And again, di is equal to basically dq over t, right? It's the same thing that we did before, omega over 2 pi dq. Okay. Now I need to say something. So I was saying this has a certain charge density rho. This is the charge per unit volume, the charge density there is, right? And so basically I have to figure out what the charge density should look like, right? Okay. So let's go ahead. This is essentially a shell-like object, right? Has a certain radius in this direction and a certain length in this direction. And it turns out that the easiest way for me to do this is basically imagine as an angle theta, all right? Okay, so imagine I'm just cutting this out as an angle theta here, all right? Right? And so dq that's contained in this region is going to be rho times the volume of this thing. Well, what is that? That's just rho, okay, times, let's give this sphere radius r. Let's see, so this distance here is going to be r sine theta, okay, and that's going to be a 2 pi times that, right? And then I'm going along here. This part is r cosine theta, but there's two of them, so it's 2 r cosine theta. Good. So that's the length, the width, and the depth is going to be dr. All right? Okay. Good. Now the area that I care about here is this area in here. That's just going to be equal to pi r sine theta entire thing squared. Okay? All right. Now, if I write this as, now this is my little r here, I'm going to basically define r in this here, so like a cylindrical r, right? So r is cylindrical, sorry. And in that case, basically r is equal to capital R sine theta, right? Because that's what that is, okay? And then cosine theta then, r cosine theta, right? Is that's just simply equal to basically square root of r squared minus little r squared. Basically this r squared sine squared theta. So 1 minus sine squared theta is cosine squared theta, square root of that, you get cosine theta in that case, right? That's where that comes from. Okay, beautiful, right? So now we literally just put it all together, right? So mu vector is going to be along the z hat direction, right? It's going to be some integral of basically a di. It's going to be some integral of, let's put everything together now, okay? So a was this, so this is going to be pi r squared, that's going to be pi r squared, that's 1. di was omega over 2 pi times dq. dq is this horrible term right here, rho 2 pi, let's see, so this is little r, this is another factor of 2 there, that's square root of r squared minus little r squared, and then this is all multiplied by dr. Okay? All right. Looks pretty horrible, right? But let's just try to simplify this just a little bit here. Okay, and I'm going to write it in a very special way in order to make this thing actually doable. All right, so let's see, the 2 pi's kill each other. So this is going to be equal to z hat. All right, there's a omega, a rho there. Those are constants out. All right, next thing is going to be integral. There's an r squared here, okay. A square root of capital R squared minus R squared. Now there's a 2r here. I could combine them and make a 2r cubed. I won't do that. I'm going to rewrite this as 2r dr. And you'll see why in just a second. All right? Okay. So this is the integral I need to do. All right? And so what I'm going to do is I'm going to basically use this. I'm going to rewrite this integral one more time. So this is z hat omega rho integral of r squared square root of capital R squared minus little r squared 2r dr. Okay, so now I'm going to do the following substitution. Let u equals capital R squared minus little r squared. du is now equal to 2r dr. That's why I kept the 2r dr together with a minus sign here. Don't forget that. And little r squared is now equal to capital R squared minus u squared. Okay? And this is going to be integrated from r equals 0 to capital R, right? So once we put that substitution, z hat omega rho integral, this is r squared minus u squared, that thing. This thing is square root of u, square root of u, and 2r dr is minus 2r dr is basically du, right? And let's not forget the minus sign in front of everything, right? Okay. Alrighty. Whoops. I messed up. This is not u squared, that's just u, okay? So that's just minus u, okay? That's why it makes things actually doable, okay? All right, and I'm integrating r equals 0 to capital R. This is integral du. Okay, so let's go ahead and do this thing. So it's basically minus z hat omega rho. All right, let's go through each one of these things carefully. Let's see, so this is going to be integral. I'm going to just drop the limits for a second now. R squared square root of u du minus integral of u square root of u du. Okay? Right? So this thing here is going to give me a 2/3 u to the 3/2 power. And this thing here is going to give me a 2/5 u to the 5/2 power. Okay? Okay. So it's minus z hat omega rho, right, times, okay, 2/3 u to the 3/2 power. What was u again? U was this thing, so that's just going to be r squared minus r squared to the 3/2 power, okay, minus 2/5. This is r squared minus r squared to the 5/2 power. Now I'm going to evaluate this from basically r equals 0 to r equals capital R. Okay? Alrighty. So this one is easy. If you put r squared, this is shown to be 0. Okay? So then you just have to just evaluate the term at r equals 0. R equals 0. And so this turns out that this will be, hold on, 1 second, I missed the extra r squared here. So there's an extra r squared there, another r squared there. Okay, so that's r cubed there. That's again r to the r cubed times r squared is r to the 5th. R squared to the 5/2 is r to the 5th again, right? So this is, and this basically, because it's on the minus sign, just flip the sign there again. And so we get basically, and I'm missing something. I missed a pi somewhere. Oh, where's the pi? I missed the pi right there. So there's a pi. There's a pi. There's a pi. There's a pi. And I'll finish it off. Pi omega rho. Okay, the sign got flipped. R to the 5th now. 2/3 minus 2/5. Look at that. All right. All that work. Z hat direction. And so, yeah. Right. Let's write this thing as, let's see, so this is 10 3s 4/15. 4/15. All right. Let's see, I'm going to write this as pi omega rho r to the 5th, right? So now if rho is evenly charged, which it has to be now, rho is equal to q, the total charge, divided 4/3 pi capital R cubed, okay? This gives you something very, very simple, actually. It turns out that this is 4/15 pi omega r to the 5th q over 4 pi over 3 r cubed 1 2 1 2, okay? 3/5 is 3/15 is 1/5 q omega r squared. Did I get that right? Yeah. Okay. So both of these work out just the same. All right. Okay. The only tricky thing was this trick up here, basically. All right. All right. So last but not least, right, I'm going to talk about slightly a different subject here, right, and that's called the Hall effect. All right. So to discuss the Hall effect, basically, if you have a bunch of these charges moving into a B field, right? So let's say you have a wire here, okay? B field, that's I here moving along. What's going to happen is that these charges will be deflected downward, right? Such that what's going to happen is that if you basically look at the size of the conductor, there's going to be slightly more positive charges on one side, and because of the absent positive charge, this will be slightly more negative, right? So this leads to basically an electric field which points in this direction, right? So this is called the Hall electric field, right? Just because there's a current that's moving through this region, right? And if this certain thing is W, right? The Hall electric field cancels downward deflection by the magnetic field. It's generally really, really small, but it is actually something that can be measured, right? So let's go ahead and see what this looks like. So if this cancels, that means that basically the electric force has to be equal to the magnetic force. So it's going to be equal to basically Q E times H is equal to QV cross B, right? Or magnitude. And so what it implies that this is E is basically equal to V cross B, roughly speaking. All right? Right? So the potential difference right? V is just minus integral of EH over the distance that we care about. That's roughly the Hall electric field times W, right? Which is the width of that conductor there, right? Okay. So what's interesting about this is that you can use this to measure the charge densities in different materials, okay? Otherwise, very hard to do. You use this to measure charge densities in material. Okay, let's see how this works, right? So, the current, you remember, is essentially the number density of charges, the cross-sectional area of this thing, each charge itself times the velocity, right? So this is number density of charge, what we're after. So what that means is that the velocity is equal to I over NQ times A, right? Likewise, the potential difference, capital V, I'll call it delta capital V, right? That's equal to E times 8, the electric Hall current times H, times W, which is the width of the conductor. Right? That's going to be equal to V cross B, right, times W, right, which is roughly, if these all perpendicular to each other, VB times W, right? And so what we have is delta V is equal to, let's plug this part in there, I over N Q A V B, oops, sorry, I got V right, B times W, right? Great. Okay. And so, hold on one second. Okay. So let's see. Right. Okay. Let's finish this off. So let's get I over n sigma. The area is the thickness times the width. So I'll call this thickness T here. T, W, BW. The W's cancel out. And so we have a nice little result here. That's delta VH, the Hall voltage, which is something that principally can be measured, is going to be equal to I over NQT times B. All right? Or in other words, basically, the number density of charges is equal to, flip this on top, I QT delta VH times B. Right? B is something you set, current is something you put in, T is something you measure, the thickness of the wire, and delta H is something you also can measure, basically by measuring the voltage across that thing, right? Okay, so right. So you can also basically measure, you can also get, or if you know N, all right, you can use this to measure B, all right? So in other words, basically you flip this thing around, B is equal to N over I QT delta VH, all right? And this Q is usually like electrons or something like that, so you should know what that is, right? Okay, so let's do an example of this. All right. So suppose I tell you N is equal to 10 to 23 per centimeter minus 3. Okay. I'm going to give it just 1 amp. Okay. This corresponds to 10 to 23 is 10 to 29 per meter cubed. Right. I is 1 amp. And the thickness is 1 millimeter, which is 10 to the minus 3 meters, say. Okay? And suppose I measure delta VH is equal to something really tiny, right? 10 to the minus 6 volts, right? So what's B? Let's go figure that out. So B is equal to N over I QT delta VH. Okay, just plug everything in now. That's 10 to 29. Current is 1. The charge is our electrons, 1.6 times 10 to the minus 19. The T is the thickness, 10 to the minus 3. And the VH is 10 to the minus 6 volts. 10 to the minus 6 volts or so, right? So if you do all that, let's see, minus 19, it's minus 22, minus 28.1. Wait, hold on, did I get it right? Make sure I do that right. No, that's it. Yeah, it's actually, so 10 to the minus 19 minus 9 is 9 minus 28. 29 minus 20 is 10. It's 10 to the 1. So it's equal to 10 Tesla. Okay. All right. Okay, so that's it for this week.